Today is all about GRPO. After this video, you will learn and understand everything GRPO related. Initially, we start with explaining what GRPO is, how does it work, what is the mathematics behind it, and why do we need reinforcement learning in the first place for the LLM training. After this part, you will have a very strong theoretical understanding of GRPO. Even though we will cover the theory, everything that will be covered here will be based on practicality. So we will do things in a way, so I will explain things to you in a way that you will be able to use in the practice, from mathematics to the pseudocodes. After this part, we will move to the actual GRPO algorithm implementation. Here we will implement the GRPO algorithm, we will implement the reward functions, we will create the data set, we will create the data loader, and we will create an evaluation script to evaluate our LLMs on predefined intervals. And actually we will train this LLM using the GRPO algorithm that we just created and evaluate it to see how much improvement we were able to achieve with our own implementation. After this, we will do a text generation example with both the base model and the model that we trained using our own GRPO script. And we will see an example that the base model was not able to get right, but the model that we trained using our own GRPO script is able to get it right. So we will have a concrete evidence apart from the evaluation scores to see that our GRPO script is actually working and providing additional capabilities to our own LLM. The theoretical details will be explained in the GRPO explanation section. So after that part, I won't go into details during the implementation. I won't explain why we use logs, why we do subtraction, why we use this formula, why we use that formula. The implementation part will be implementation focused. If you don't understand something theoretical, even though I will connect the theory and the practice part pretty well, just go back to the beginning of the video and watch that section. I will put all the codes and every resource that I mentioned in the description of this video. You can check it out from there. And make sure that you hit that like button, subscribe to my channel. What you wanna see next, let me know in the comments. And let's actually get started with the video. Let's start by explaining GRPO. So what we will talk about is, first we will talk about why do we need reinforcement learning in the first place, why SFT is not enough, why we are doing this. Then we will continue with what problem does GRPO solve and why it was invented in the first place. Because before that there were still other reinforcement learning algorithms for LLM trainings, but why did GRPO came up? And then we will actually go with the technical details. So GRPO is an algorithm. First of all, we will look at how do we calculate the loss of the GRPO. We will go into details of mathematics, but it is not heavy, it is very straightforward. And I will explain it in a very understandable way. So bear with me at this point. We will take a look at log props, we will take a look at the surrogate function, and we will take a look at the KL penalty, which are the elements that make up the GRPO loss. And after that, we will actually go and look at the GRPO algorithm and its pseudocode. And this will be the actual GRPO. And we will do all of them with practicality in mind. So instead of just theoretically defining functions and just letting them stay on the paper, we will actively connect them to the code. So this math will be the practical math and the pseudocode will be a practical pseudocode. And actually when we switch to the coding part, we will implement this GRPO loss by implementing these formulas that we will discuss here. We will discuss here exactly one in one. So there won't be any change there won't be any, like, this is how we did in the formula, but we are changing this in the implementation because it's more effective, or this, there won't be that thing. So when we look at the math and when we look at the pseudocode, everything will be with practicality in mind first. So let's continue with, why do we need reinforcement learning in the first place? So the first question is, why SFT is not enough, and why do we put reinforcement learning on top? In its core, SFT is kind of imitation learning. So what do I mean by that is, we have a data set, we have questions, and we have answers to them that are prepared by an expert, or like synthetically or whatever. But what the model learns is that it tries to imitate that answer as good as possible. So it is just cloning the behavior that already exists in the data set. In this data set, there is only one correct answer, and actually one answer only. So what happens is, especially with the tasks such as reasoning or tool calling, is that the model cannot discover anything new. It only learns how to copy what is in the data set. So maybe there is a question, that like a mathematical question, and there are more than one ways to answer. Let's say that there are 8 different answers and 3 of them are correct. However, with the reinforcement learning, the model generates its own answers and then tries to put on top of that. So what it does is that actually the model starts to discover how to reach to the correct answer, and usually there is more than one way to reach the correct answer. And it continues to discover how to make a better reasoning, how to make a better tool call, etc., which is very limited with SFT. For example, we gave a math question and the model may generate 8 different answers. And these answers are discovered by the LLM itself, and it is not part of the data set. Then the model will see that 3 of them are actually receiving positive signals. So it will say that I'm on the right path, so I should reinforce that behavior further. And it starts finding strategies such as maybe I should verify this result before answering, or maybe I should check if the API is working correctly, or if API is not working correctly, maybe I should fall back to something else. With SFT, it is not really the best way to do these things. Additionally, with SFT, you have a limited space where you learn things, and when you move out of that, LLM will not know how to behave in that new data distribution, because you only taught it with the dataset you trained with the prepared answers, and the model basically only knows how to imitate those answers, or like a clone those answers in that distribution. With reinforcement learning, when we do the reinforcement learning, the model is actually generating its own answers, and it is able to move and make decisions when there is a new environment that it should make decisions at. So this is what I mean by saying SFT teaches the LLM to reproduce the behavior that's currently in the data set. And with reinforcement learning, we actually encourage the model to discover new things, to discover what is working, what is not working, etc. So for example, an answer is, what is the weather tomorrow? User might ask. And in that case, there are many ways to extract how the data is. There are many trajectories. So for example, you may want to call the weather API and then see the location of the users first, and you want to extract the data of the tomorrow's weather, inspect the hourly forecast, and do some verifications on the answer, maybe ask some follow-up questions to the user, and answer it in the end. So in case of reinforcement learning, the model can do that, and if it reaches to the correct answer or whatever your verification rule is, this behavior will be reinforced and it will actually try different things. Maybe it won't ask a question to the user if it sees that it is performing better this way. But with SFT, there will be only one answer and one answer only, so the model won't be able to actually discover anything, experiment with anything, and it is just tied up to the what is in the dataset initially. So a good analogy is in here. So SFT is like you are taking a driving class and you are just watching the driving instructor, and you see that at the intersections they brake here, they turn the wheel this much and they accelerate, etc., and you have a base to drive actually. But when you are behind the wheel, sometimes you have to accelerate in a different place, there's a different corner, there's something else that you need to do, or you have to check where the other cars are, there's a different road, there are different rules, etc. With the reinforcement learning, you are actually getting behind the wheel, driving in the new environments and learning in the meantime actually. And by this, you actually learn how to become a better driver instead of just staying with the knowledge that had been taught to you at the driving classes. In practice, before reinforcement learning, we usually apply SFT. So what is the reason for that? You have to think back of what we have talked about with SFT and reinforcement learning. So for reinforcement learning to work, you need some set of correct behavior to begin with so that you can reinforce it. Let's say that there is a question and you made 1,000 attempts and 150 of those 1,000 attempts are correct. So you reinforce those 150 attempts and you discourage the behavior that didn't produce the correct answer. And how those 150 correct answers emerged initially is that it is with SFT. You did some SFT and the model produces actually correct answers, and you can reinforce those correct answers to make the model better at whatever you are training it at. But let's say that you haven't done the SFT and you have 1,000 attempts, and out of those 1,000 attempts you get all of them wrong. In that case, you have nothing to train. You have no behavior to reinforce. So let's say no SFT, 1,000 attempts, 0 correct. So you cannot actually reinforce anything. But say with SFT, you have again 1,000 attempts and you have 150 correct answers. So you can reinforce that 150 correct answers, and in the next iteration you may have like 200, 300 correct answers, and then you reinforce that, etc. It goes like this. And one other thing is, unlike SFT, where you go token by token and you reinforce that and you teach the model to actually use that token after that token after that token, with reinforcement learning, what we care about is what is in your reward, which usually is if the final answer is correct and a couple of things that the model may do while reaching the correct answer. So there is much more freedom for the LLM to discover new things and learn on its own. So this is why do we need reinforcement learning in the first place. So what problem does GRPO solve and why it came out in the first place? So initially, if you want to compare it with something, we have to compare it with RLHF because it is widely used and it was before GRPO, and it is also a reinforcement learning algorithm. So why GRPO but not RLHF? So how RLHF was working is that you have a rollout, and what rollout means is that basically what your model generates from the prompt that you give to it, because you don't have a gold data set or like correct answer in your data set, you only have the prompts. You give that prompt to the model and it generates you an answer, which is called rollout. So with RLHF, what would happen is that you would compare that rollout against a critic model. Critic model is usually just another LLM without the LM head, and it would give you a score which is its expectation, and this would become your learning signal. So you would decide whether to reinforce the behavior of that rollout depending on the feedback that comes to you from the critic model. So one thing to notice is that there is an additional critic model, which is one of the keys. In GRPO, however, you compare the rollout against average of rollouts generated for the same prompt, which we call a group. So you have a prompt, and with GRPO, from that prompt, you generate multiple rollouts, multiple answers. You take each rollout and compare it with the average of the rewards that are generated from the same prompt. So if it is a bit abstract right now, don't worry, because we will make it more concrete with the mathematics, and then also with an analogy now, and then we decide if we should reinforce the behavior of that rollout or not. So instead of a critic model, you compare each generated text with each other, and this is called a group. Let's say that you generated 8 rollouts, 8 texts from the same prompt. Those 8 texts becomes a group of size 8. So one thing that GRPO does is that it gets rid of that critic model, because it is comparing the rollouts with each other. So this is especially important if you think about it. If you train a model with like trillions of parameters, having another critic model with trillions of parameters would take a lot of memory. With GRPO, we don't need it. But another thing is, with GRPO, in practice, we generate multiple rollouts for a single prompt. So what happens is that especially in tasks like reasoning and tool calling, if those rollouts are long, you have to store them into memory as well. So you are getting rid of the critic model, but also you're introducing more rollouts to store in the memory. So there is a trade-off there, but in overall, GRPO is much more efficient. A good analogy that I see with the GRPO and RLHF, think of a student taking a school exam. So with RLHF, you can think the student as your policy model. What I mean by policy model is that LLM you're training, and if you start calling it a policy, then congratulations, you are in the RL territory. So in RLHF, you have a policy model, and which is the student, and student answers a question and gets a score, and that score is the reward that it is getting. And there is a critic model, which is the teacher who estimates how well the student was expected to perform on that question. If the student does better than the critic, which is the teacher expects, the teacher says, okay, that was better than I expected, and keep doing what you're doing that led you to this result. And the critic model tells the student that it is doing well, so student will continue doing that well. But if the student model or the policy does worse than the teacher or the critic model expects, the teacher says this was worse than what I expected, and in the future try to avoid the behavior that led to this result, which discourages that behavior. In GRPO, we remove the teacher. There is no teacher, aka there is no critic model. Instead, we let the same student attempt the same question several different times, where each attempt we call a different rollout, which are different answers. So student provides like 8 different answers for the same question. Maybe it solves the problem with a different way, using a different formula, etc. and maybe in another attempt he does a mistake and gets the wrong conclusion, but in the end he tries different answers. And then we grade all those attempts and compare them with each other. And if one attempt performs better than the other attempts, then we say this rollout was better than the other rollouts. So keep reinforcing that, whatever strategy you follow to solve that question. Maybe you verified your answer before answering, maybe you used a different formula, maybe you used a calculator, etc. Whatever you did, it is better than the average of the other answers you provided, so keep doing that. And if another attempt was worse than others, then we say don't do it. Maybe you just put the number that you like as the answer, or like you chose the closest selection. Whatever it is worse than the other attempts you have tried, which is the other rollouts within the group. So don't do it, and we discourage that. And in the future, the student keeps whatever it is working and just doesn't do whatever was discovered and was not working. And both approaches trying to answer the same question: was this behavior better or worse than we should expect? RLHF answers that using a learned critic, whereas GRPO answers with using other rollouts, other answers that the policy or the student has generated. So this is the overall difference between GRPO and other reinforcement learning algorithms, such as the popular one, RLHF. And this is what GRPO solves and what it does differently. And now let's actually start to go over the core of GRPO, which is its loss function. Within the GRPO paper, DeepSeek gives a compact mathematical expectation, and it hides many of the concrete operations required in the code. And we don't want that, because here we are all about practicality and to see how we can make things work instead of just doing the mathematics. So here I expanded that formula into an implementation level. So here it is. And another thing is GRPO gives this, the DeepSeek paper gives this as an objective to maximize, which is true because we want to maximize the reward we are getting. But in practice, what we usually do is we try to minimize the loss function. So to do that, we can just multiply it by -1, and we try to minimize the loss instead, which I already incorporated in this loss function. And this is important in practice because it makes easier to interact with libraries such as PyTorch, TensorFlow, or whatever you're using. So because of that, because we are trying to make things work both on the paper and in the code, we will use this formula that is much more appropriate for implementation. Another thing I forgot to mention is actually the original formula has this thing. So we have written as 1 divided by n, where n is the total number of tokens. Originally it goes like this: 1 divided group size. We sum everything from I equals to 1 to the group, and then we divide by 1 to the ti, and we sum everything within the t equals to 1 to the ti. And the rest of the formula is the same, which is minus sit theta, which is the surrogate function, plus beta multiplied by dit, which is the KL penalty, theta. So what is the difference between this and 1 divided by n and adding up g and ti? The difference is the bottom one, the one that we are going to implement, adds everything up first and then divides it by the total number of tokens. The upper one, however, first adds everything up within the rollout, divides it, then adds them together and divides it by the group size. So the thing about the top one is that if one of your rollouts is shorter, the tokens in that rollout will have more effect on the loss value. So what I mean by that is, think about you have two rollouts. Rollout 1 has a length 2 and rollout 2 has a length 8. So with the original formula, surrogate for the first rollout is, let's say it S1, S11 plus S1 plus S12 divided by 2, and the score for the second one rollout is S21 plus S22 plus, it goes like this until S28 divided by 8. And when you think about it, each token within the S1 has a weight of 1 divided by 2, whereas each rollout in the S2 has weight of 1 divided by 8. So doing this, each rollout, each token in the S1 will have 4 times more impact on the last value because of its weight compared to a token in S2. So what this does is that if you have a shorter rollouts, every token in the shorter rollout has a greater impact on your final loss value. So even though in the end we divide them by 2, which is the number of group size, we normalize each token by token length, and the rollout with the fewer tokens naturally gets shared that weight among fewer tokens, so that token has a greater impact on the last value. So this is the overall idea. However, if we just divide everything by n, total number of tokens in the end, it doesn't matter if the rollout is short or long, every token will have the same impact on the final loss. So this is the difference between the original version and what we use. So why we use 1 divided by n? Oh, this is a choice, okay, and this is usually what the modern implementations use as well. You divide it by 1 divided by n in the end, and easy to implement. So we are going with the 1 divided by n instead of the original, dividing it by number of tokens and then dividing it by number of elements in the group. So when you look at it, you will realize a couple of things. So let's start with inside. So this guy is your KL penalty. We will discuss more about this, but it just prevents the model from changing its behavior from its original version to some extent, so that the model can learn new things but also can stay close to its initial version, which we will call the reference. We will talk more about this, and this is our surrogate function, which you will see is just PPO. And we are adding these up, and we are trying to minimize the final loss. What T here is that it is the T token within the generated rollout I, and what G is that it is the number of groups. So what these two sums does is that first you iterate through the group, which you iterate through the rollouts, and then you iterate through each rollout. And for what this means is that within the group, for each token, we have to calculate this value and add them up, and in the end we divide it by n, and n is the total number of valid generated tokens within the current group. And this is basically the GRPO loss. It's very simple, just two parts. You have the surrogate function, you have the KL loss, and this beta is just a hyperparameter to scale the KL loss. Hyperparameter. You do it for every token, you add them up, and you divide it by the number of tokens in your group. Very simple, very straightforward, and very short as well. And now we have to actually expand it a little bit. So the first thing we will look at is the log props. So it is important to understand here what are we doing here, why we are using logarithms, and where will we use them. But first, let's understand what these are doing. So you will see three different log probabilities, which are all the same. The only thing that differs is the model that we are using, which is p theta. So the p theta is the model that we are currently training. P theta alt is this can be a bit confusing, but it will be much easier to understand when we look at the code. So p theta alt is the model before we do the PPU updates, okay? And also it will be much more clear in the pseudocode as well. So within the GRPO algorithm, you will do PPU updates, and before beginning that PPU updates, the model in that state will be p theta alt, and after PPU updates, the model will be p theta. So, and the pref is just the model that we had in the beginning of the training, which we call the reference model, and it will be used in the KL loss. So what this formula says is that take your model, p theta, and within that model, what is the conditional probability of generating the token Y within the rollout I, so I is your current rollout. And for the position T, which is the position that you are currently generating, giving that X, which is your prompt, and all the tokens that you have generated before the current token, which is less than T, for the current rollout of the group. So what it is saying is that what is the probability of generating the next token T, giving prompt plus everything you have generated so far. So it is simple as that, and it is the same for every one of them. It's just next token generation with the given prompt and everything that is generated before. And now the question is why we use logarithm. So the thing is, with the surrogate function, we want to compare the ratio of new probabilities divided by old probabilities. So this is what we want to do. But we have a problem. If we do it directly like this, it may be numerically unstable. For example, let's say that your new prompts is 1.1 10 to the minus 20 divided by just 10 to the minus 20. So your new log prompts is 1.1 multiplied by 10 to the minus 20, and your old prompts is 10 to the minus 20. So the answer is pretty simple. It is 1.1, right? But in practice, if you are working with limited precision with the floating points, they may become both 0 because of 10 to the minus 20 will overflow, and as a result, what you will have is 0.0, which is non-value, which is not something that you want. So we have to solve this problem somehow when comparing these probabilities. So one thing we can do is, there's a property of logarithm which is b to the logarithm bx is equal to x. So we can actually use that, and in this case our x is new props divided by old props. So what this can be is that e to the ln new props divided by old props, which is, we can just say exponential, which what we will do in the code as well, exponential ln new props divided by old props. And because we are working with logarithms, we can turn that division into subtraction, and it becomes exponential ln new props minus old props. So this and this are equal to each other. Now let's try the same numerical example with our new formula. In this case, ln of 1.1 multiplied by 10 to the minus 20 turns out to be minus 45.96, and ln 10 to the minus 20 turns out to be minus 46.05. And I forgot to put ln here. There is ln in here. So when we plug it out within the formula, what we have is exponential of minus 45.96 minus 46.05, which is equal to exponential of 0.09, which is more or less equal to 1.1. So we reach the same conclusion with this formula without worrying about the overflow. So that is the idea why we are using logarithms here. And here we calculate this first, so that this, for example, will be our new props, this will be our old props, and when we are doing operations, this ratio operations using exponential logarithmic form, we will just be plugging these in. So this is why we care about the log probabilities, and we will just, for the numerical stability, and we will just calculate them in the beginning, and we'll be plugging them in to this exponential formula to get the probability ratios. And why we will need probability ratios, now we will explain that within the surrogate function. So this is the surrogate function, is the PPO basically, and if you're familiar with it, you will just directly realize it. So we are trying to minimize our loss, and when we look at the formula, if we want to minimize this loss, we have to maximize this, our surrogate function. So this is our purpose, to maximize the surrogate function. And the surrogate function is basically this ratio, IT theta divided by advantage I. I will tell you what advantage I is. And RIT, we actually already learned about it. This is RIT. Ratio of new probabilities divided by old probabilities at ith rollout and t token, until the t token. And we already know how to do it. So yeah, I put it into here too. Probability ratio is the comparison between the new probabilities and old probabilities. So like I mentioned, this is just the new token generation within the ith prompt until the prompt T, and we include everything before the prompt T within the ith rollout. So it's basically new probabilities, and this is basically old probabilities, and this is equal to this, and we actually showed it here mathematically why it is equal and why we are using this logarithmic form instead of the regular ratio. And to make things more simpler, instead of writing the whole logarithm of new prompts, logarithm of old prompts, we are just using this. For example, this is logarithm of new prompts, this is the logarithm of old prompts. So L theta, L old, theta is by like there's default, which is the trainable parameters, but this is just the like new log props, and this is the old log props. So these two things are equal, and we are using this one for the numerical stability. So this is the R. I will explain the advantage after this, so don't worry about it. It is also very simple and straightforward. And this is again the same thing, which is we just take the ratio, but it's clipped version, and multiply it by advantage. So the clip is that so that we will have some sensible values. Okay, like this is the main idea of PPO. We don't want to overshoot, we want to take like smaller steps, and this is what this clipping makes sure that it happens. So it's basically we take the minimum of these, which are multiplication between this ratio and advantage. So it's that simple. You just multiply ratio and advantage, and in the other you clip it and you get the minimum. And like I said, we will use this exact same formula in the implementation as well. So maybe this all like this I's and T's and this operations may become more easier to understand within the code as well. So advantage. What is advantage? Actually, I will do this slide first. So what is advantage? Advantage tells us how well this rollout performed compared with other rollouts within the same group. So it is our main learning signal. Like I said, when we compare the rollouts, we have to be comparing something, and we are comparing what is called advantage, and it tells us how well this performed compared to other rollouts. If this advantage is positive, we reinforce that rollout behavior. So we say if that rollout is able to get a positive advantage, it is doing something right, and we want it to keep doing that. If the advantage is negative for that rollout, it means that that rollout is doing something wrong, and we want to discourage that behavior. And why does this work within the formula? Why, if advantage is positive, that rollout gets reinforced, and if it is negative, that gets discouraged? So for that, we have to look at the surrogate function. So let's start with if advantage is positive. Okay, in that case, so remember we are trying to maximize this value, right? If advantage is positive, then to maximize this value, we have to maximize this ratio IT theta. And to maximize this, we have to maximize the new probabilities, and the new probabilities are basically what is generated in that rollout. So with positive advantage, we are basically maximizing the new probabilities. Let's say that advantage is negative. We are trying to maximize this function, and in that case, to maximize this function, we have to minimize the ratio. And how do we minimize the ratio? We reinforce the old probabilities, so we want old probabilities to be higher and new probabilities to be lower. So by doing this, when the advantage is negative, we discourage this new probabilities, which whatever the LLM did in that rollout. So this is why this behavior is happening. Positive advantage reinforces that rollout behavior, which is the new probes, because we are trying to maximize the surrogate function. And a negative advantage discourages that rollout behavior because, again, we are trying to maximize a surrogate function, and to do that we have to minimize this ratio, and to minimize that ratio we have to discourage the new rollout behavior. And the larger the magnitude of the advantage, the stronger the learning signal. Actually, we just discussed this, why advantage behaves this way. So now, how the advantage is being calculated. So every rollout receives a reward, which can be based on anything. So let's say that if your LLM gets the correct answer, you have the reward 1. If it gets the wrong answer, you have the reward 0, okay? But on its own, it is not really meaningful, because let's say that you have several rewards, like you have group of 4, you have rewards 4, 3, 2, 1, and based on the rewards, you have to reinforce them all, right? It doesn't make any sense. So we need something else. We need a different learning signal, which is advantage, okay? So this is what the GRPO is all about. So how we do it is that we get the reward, current reward of the rollout I, for example 4. We get the mean of the rewards of that current group, which is in this case 4, 7, 9, 10, 10 divided by 4, which is like 2.5. And we divide it by the standard deviation plus a small constant we add so that we prevent the division by 0. So let's say that in this case, this becomes 4 minus 2.5, which is 1.5, 3 minus 2.5, 0.5, 2 minus 2.5, minus 0.5, 1 minus 2.5 is minus 1.5. For now, let's just don't worry about this division, okay, this normalization. And these are the rewards, and these are the advantages. Now, if you look at it, we have a meaningful learning signal, because we know that this rollout is doing better and this rollout is doing worse, even though both have a positive reward. So what the algorithm will do is that it will reinforce this, whatever we did in here, and discourage that instead of reinforcing all of them. So this is what the advantage is all about. And this is how we calculate it. Very simple. And this is why we need advantage. And advantage behaves this way. And the reason for that is, like we discussed, to maximize the surrogate function. Now, if we put things together for the surrogate function, I think it would make more sense. If this guy is positive, we have a positive advantage. We want to maximize the surrogate in all sense. And to maximize this, we have to, in the case of a positive advantage, we want to maximize this RIT. To do that, we have to maximize the impact of the new log probabilities. So we encourage that. If it is negative, we do the reverse. We have to minimize this. To minimize this, we have to discourage the new log probabilities. And the second one is just basically the same, but with clipping. So this is the surrogate function, which is the main part of the GRPO loss. And it has two parts, the ratio and advantage. And That's all. And now you know how both of them behave, how both of them are calculated, and soon you will do the same things on the code. So now, if we look at the loss again, we have covered this surrogate function, and now the second element is the KL loss. So let's do the KL loss too. Or KL penalty, which is more correct, I think. So for this, to calculate the regular penalty, GRPO uses something called Schulman's K3KL estimator, which is this guy over here. So the question is why we are using this instead of just regular KL calculation. And the reason is that regular KL divergence will require us to go over the full vocabulary with this formula. As you can see, we are going through the full vocabulary, but this requires a lot of calculations. So in reality, we already have a sample. We already have an Y that we sampled from our current policy. So instead of going all over this, we can do a much cheaper estimate. So there may be many estimates to do this, but for GRPO, the Schulman's K3KL estimator is used, which is this guy. And as you can see, we are using the log probabilities in this estimate as well, which we already calculated in the beginning. So this is why we already also calculated the log probabilities for the reference. So this is basically telling you how much your new model diverges from your current model. And this value is always positive. Why is that? Because exponential always grows faster than this guy. So this is always positive. And actually we can do like a quick math to see like how it behaves between like two models. Let's say that our reference model and the theta model are the same, so we haven't made any change. So the KL divergence should be 0 because they are the same model, so there is no divergence and no difference between them. In that case, this will be the same, this LREF and L theta, and exponential it would be e to the 0, which is 1. And we already mentioned this is also 0, so it would be minus 0 because they are the same, minus 1, which would be 0, which is the correct thing because they are the same model, there shouldn't be any divergence. And this is just fun math. And one assumption I made here is that you know what KL divergence is. I won't go into detail. It is just a value that tells you how much two models diverge from each other. So why we need this KL loss in the GRPO? And how does it work? So how it happens is that as your surrogate function gets higher and as you increase the new log probabilities, you diverge from the reference model and you learn new things basically. But what may go wrong with this is that it is increasing the log probabilities based on advantage that is calculated by the reward. And you calculate the rewards by a reward function or a reward model, and they are not perfect. If you don't try to make it stay close to the policy model, to the reference model, your model can easily learn new ways to get high rewards with behaviors that you don't want, which is called reward hacking. So let's say that maybe you don't want the model to use parentheses when it answers, but also you want the model to actually talk normally, right? So without getting close to the reference model, what the model can do is that it may just generate the same letter A 1000 times, and it will get a full reward instead of generating a sensible information. But if you put the KL loss, the KL loss is kinda pulls it in to the reference model. So it will keep the behavior of the reference model, which is generating coherent text, while trying to maximize the reward, which is not putting parentheses. So when you do that, instead of generating 1000 A's, it will actually generate a sensible text while trying to not put the parentheses, and tries to get a high reward like that instead of a hacking behavior such as like putting the letter 8000 times. Or it may learn to generate unnecessarily long text, nonsensical response, so that it just found out that when it does that, it gets a higher reward. There can be other forms of policy drift, such as entropy collapse, overfitting the RL training dataset, degradation of the model's language capabilities, etc. So what KL does is that it pulls it back to the reference model so that it keeps the behavior, the coherent behavior it has in its root. In the end, what this loss is trying to do is that it is trying to find a balance between learning the new behavior and staying close to the reference model. So if we stay too close to the reference model, we don't learn anything new. If we don't get close to the reference model and just like maximize the reward always, there can be huge policy drifts. So with this, we are trying to find the middle ground and like the balanced way in between, such that the model is coherent and still maximizing the rewards so that it is generating the behavior that we want. So this is why we use the scale penalty within the formula. But it is not a must. If you look at the frontier models, you will see that KL is usually being removed. So one disadvantage of KL is that you see here ref. So you need to calculate the log probabilities of the reference model. So you have to load the reference model into the memory. So you have to load one more model into the memory. And if you are dealing with the models with trillions of parameters, it is a big setback. So this is one thing you don't want. And the other thing is, let's say that you want your model to actually be better at like chain of thought. To do that, you want your policy to move farther away from your reference model so that it learns this chain of thought in better ways, like it can comfortably do the tool calls, etc. And removing the KL gives the policy this freedom to explore the new behavior and continue to improve without the restriction of the reference model. However, you have to be careful if you want to do that, because it can easily go into the territory of policy drift. So usually you have to be careful with some things if you want to remove the KL. So the training overall should be very stable. The reward should be like very stable. Maybe like it can be checked mathematically, it can be unit tested, it can be validated, and it is harder to exploit and it is harder to reward hack. And you have other controls such as clipping, small learning rates, and you carefully monitor the training so that the rewards are fine, validation accuracy, entropy is fine. In those cases, it may make sense to remove the KL altogether so that the model can explore more freely and the model can diverge from the reference model without any restrictions. And sometimes the KL term can prevent learning. It may pull too much to the reference model, so reward stays still, policy barely changes, and no useful new behavior emerge. It is because the KL is pulling your model too much to the reference. Because of that, your model is not able to learn any new information. So in that kind of scenario, it also makes sense to remove the KL loss. And also, like we mentioned, there is the cost of loading the reference model into the memory. So this is the GRPO loss. how we calculate it and why we calculate it, and in what scenarios you can actually think about removing, and why frontier models are actually removing the KL penalty. But within the implementation, we will add it because we want to see how things work, and we don't really have a very stable training pipeline too, so we will need KL penalty. So when we put all things together, again, let's look at the formula. For every token inside every rollout, we are calculating the surrogate function, and we are adding it with the KL loss with hyperparameter beta to control the scaling. And we divide it by a total number of tokens, and we have the GRPO loss. It is that simple. Now we are at the last part of explaining the GRPO algorithm, which is actually the algorithm itself. Now I prepared this pseudocode, and I think this is a very good pseudocode because within the implementation, we will just follow this 101. It is a very solid pseudocode. It uses the math, and it shows you the math, and we can just translate it to the code directly. And it is very understandable. So we start by having the reference policy, which we just copy the policy, and we traverse the data set. So we'll have a prompt within the data set, and we start generating rollouts. So we will have a function for that, and we will give our policy model, we will give our prompt, and we will give the group size, which is the number of rollouts to generate. Like we discussed, we start by calculating the log probabilities. So the old log probabilities, we will have a function called log prompts, which will take policy, prompt, and rollouts, and it will return us the log probabilities. So we give the policy before this loop, so it will be odd log probabilities. We give the reference policy, so it will be our reference log probabilities, and then we will calculate the rewards for those rollouts, and we will have a function to do that. And then we have to calculate advantage, and we will have a function for that too. We will give the rewards, and it will return us the advantages. And then we will actually do the gradient updates. So we will have hyperparameter called PPO epochs, which is the number of times you want to do this update. At each time you will have calculate the new log probabilities. So initially this will be equal to your old ones because you haven't done any update on the model. Again, the same function, log probabilities, which has policy, prompt, and rollouts. And then we calculate the ratio, which we discussed. That is exponential of new log props minus old log props, 100% the same formula. And then we get the surrogate function, 100% the same formula. We multiply ratio by advantage, and then we multiply their clipped versions and then get the minimum. We calculate the KL penalty, which is again the same formula, exponential of the difference between log props and regular difference of the log props minus 1. And then we take the mean because we want to divide them by the number of total tokens. So minus surrogate plus KL coefficient, which is beta we discussed, multiplied by KL, and we get the mean, and this becomes our loss, and we update the policy with that and repeat this loop for PPO epochs times. So if you realize there is no INT, because we are already working with matrices, they are already encoded in that, so we don't have INT, but it is already inside this like surrogate, KL, whatever, in the form of matrices. And this is the GRPO algorithm, and this is the old GRPO. And now we know in theory how this works. The next sensible thing to do is actually make it work in practice, implement this, train a model with this, and see if it is actually working. Okay, now it's time for the implementation. Before we start, I will do this implementation inside this repository called post-training lab within my GitHub. So what this repository is that I implement these post-training things in a very minimal and understandable way. But to follow this tutorial, you don't need it. Okay, you can just use the standalone script that we will create, and I will put it under the tutorials here. Like I said, you can just follow this and you don't need this repository. It is not mandatory, but I recommend you having it. What I recommend you to do is just clone this repository and go under tutorials and create a new Py file and follow there, or just follow it through the file that I will upload there. The reason is you will be able to just copy paste the exact commands I do, and at the end of the training we will do some text generation. For that I will use some of the scripts within this repository, but you can still just copy paste them and do it in somewhere else. So it is not mandatory, but I think it would be easier to clone it and put it under the tutorials, also for the dependency wise. But like I said, you don't have to. You can just follow the code with me and just run the code with a different command, and that's all. So I will be doing under this repository, so I will be running the commands accordingly, etc. If you're on another repository, just change the commands and you should be fine. And as you can see, now I have a GPU at home. I have a 16 gigabyte GPU, so I will be actually using an IDE instead of a cloud provider. So I'm very happy about it. And a couple more notes before starting. At the first section we will do the dataset. Okay, we will do dataset preparation. So obviously it is needed for if you are doing an LLM training. We will write some evaluation scripts to evaluate our LLM, both on the test set and both on the validation set. So this is, like I said, a end-to-end pipeline, right? We train it, we evaluate it, and we will generate text with it. But if you're just interested in GRPO part, you can just skip the dataset preparation or the validation parts and just go for the GRPO and the reward function definitions. But I recommend to have a good grasp on the whole process. And the other thing is we will be doing the training with LoRa, because I don't have enough computation power for a non-LoRa full training, and this code is not optimized for efficiency anyways. It is optimized for simplicity and learning. But if you don't want to use LoRa and you want to do the full training, you can just remove the LoRa from the code and it's going to work. Okay. And everything apart, let's actually start. So we will initially start with library imports. We will use copy for copying the original model to reference model. We will use operating system for some saving things. We will import random for random seeds. Unfortunately, we will use regex. We will need NumPy. We will need Torch. We have to load the dataset. We will load it from Hugging Face. For LoRa, we will use PEFT. And to create the dataset, we will use PyTorch, data loader, dataset, and random split. For progress bar TQDM, we will load the model from transformers. And those are all the necessary libraries. For the model, I will be using Qwen2 0.5p instruct because it is not fine-tuned on reasoning. So we can just take that and see actually what effects, what capabilities we are making it gain on reasoning or math, which is the task that we are going to work on. We will work on GSM-8K, by the way. And it is also small, 0.5p, so it fits into my lovely GPU. So group size, I will do 4. So as you remember what group size is, how many rollouts does the model generate from a single prompt, meaning given a single prompt, how many answers your model will generate. So I set it to 4. Maximum new tokens is the maximum new tokens that the model is going to generate. I set it to 256. It is a good number for GSM-8K. Learning rate, I set it to 1e-6. KL coefficient, this is also what we discussed. Just before the KL, we are multiplying with beta. So that beta is KL coefficient. And I set it to 0.02. Clip epsilon, again, when we discussed with the surrogate function in the clipping, there is an epsilon that we add and subtract. So this is the value I gave to that epsilon for this run. PPU epochs is the number of PPU epochs we will do. We discussed this during the pseudocode. So for this one, I set the PPU epochs to 4. Number of iterations, this is the total number of iterations that we will do over the data set. So we will just do 200, and with 200 iterations, we will be able to actually see the effects. And the training should run like a 1 hour. It is not a long training. This epsilon is the epsilon of the advantage calculation. We discussed it during the reward calculation. This is to prevent non-zero divisions. A lot of epsilons. And these are the hyperparameters. And for LoRa range, for this I set it to 8, LoRa alpha 16. We will set the seed to 42 so that these results are reproducible. And during the training, we will also do validation so that we can see the improvement on the validation set. For the validation split, I set it 0.05, very small validation split. And max prompt length is if the length of the prompt within the data set is less than 512, we will include it. If it is more than that, we will exclude it. So I did it so that there's no very long prompt that we will have to process, and it will give us an out of memory error. And we will evaluate at every 50 step. So we will get a validation score at every step 50. The batch size for the evaluation will be 8. And at every 100 step, we will save it. And we will save it under checkpoints, tutorials, GRPO minimal PyTorch. So in my case, it is here, it's just under checkpoints and tutorials. I already did a run. So it will be saved in here. For the data set, we will be using GSM-8K. The Socratic split, I just chose this one, and obviously we will use the train split. Next, we have some regex. Obviously, I didn't write them. They are AI generated, but we will use them to basically extract the answer from the text. So just keep them. And there are other couple of functions that we should put before starting. The first one is set random seed. So this function will go to the operating system, to random, to torch, and set up the random seeds for us. So there's nothing much to explain here. Now the next step is loading the models and the tokenizers. For that we will define a function called load policy and reference. Loading the model. So our policy is, we just load it like a regular Hugging Face model from pre-train. SD type bfloat 16 is fine, and we wanted to put it into the GPU. And we want to load our tokenizer. And if pet token is none, we want to make it equal to end of the sequence token ID. By the way, there may be some tokenizer related differences if you use another model, like other than Qwen, something else. So keep it in mind. I haven't tested with other models. Like the algorithm is the same, it should work. There may be some tokenizer differences that you should resolve. But for Qwen, these setups are working. And now we put our LoRa configuration. Task type is causal LM. R is LoRa range, LoRa alpha, LoRa dropout, and target modules are all linear. And we are applying LoRa to all linear layers. So we do this by get path model, policy, and LoRa config. These are all library related things. Next, we put the policy into the evaluation mode. It may be a strange thing, but we do it for consistency so that during the forward pass, it will produce us the same output no matter what. So this is the reasoning for that. And we copy the reference model from the policy. We do it with deep copy. And for the reference, we obviously don't need gradients, so we set it to false. And we also put it into evaluation mode so that it is deterministic, just like the policy. And we will just sum up the trainable parameters. For that, we count the parameters, and for every parameter, if it requires gradient, if it is trainable, we sum them up. And we can calculate the total number of parameters with this list comprehension. And then we will just print that we are training with LoRa, and this is the number of trainable parameters out of all the total number of parameters. And we return the policy, reference, and the tokenizer. So this loads our model, our reference model, and our tokenizer for us. Now we can start constructing our main function. So let's define the main. So we create, if it doesn't exist, we create a directory for saving the checkpoints. We set the random seed with the function that we just created. And we load the policy and the reference model and the tokenizer again with the function that we just created. And we have to select the trainable parameters. So this is important for LoRa because we will feed this into the optimizer. So again, we can just use the same thing. Parameter for parameter in policy.parameter. And if it requires gradient, we just add it into the list. And then we create our optimizer. I will use AdamV for this. So we pass trainable parameters only since we are using LoRa. And we pass the learning rate. And that's all. Now we have to add some helper functions that we will use in the dataset. I know, very boring, but we have to have data to do the training. So I will do these as quickly as possible. So we will have a function called load rows, and it will just get the dataset split, and it will just return us the dataset. Next, we will define a function called normalize number. So what it's going to do is it will normalize the numbers. What I mean by that is, let's say in the string form, it may say the answer is 1.0, but the answer is actually 1. So they are actually equal, but for the computer they are not. We want them to be actually equal, so this is what it's going to do. So it will just remove white spaces, separators, decimal points, etc. For this, we take the row number, strip it, and replace the comma with nothing. So we remove the comma. And we remove the suffix dot. So we remove the suffix dot. It only removes if the string ends with a dot, like 122 dots or whatever. It removes the dot. So it is an additional small formatting step. Next thing is extracting the answer of the GSM8K from the string that we will get. For this, we will define a function called extract GSM8K answer. It will take the text. So a regex warning, first of all. And the second is it will extract if the answer comes after these 3 hashes. So there will be actually another extractor that will extract the most likely answer even though it doesn't end with the hash. It is important because at the end of our training, even though the answer is correct, it will not always end with hashes because we will not do a very true SFT to teach this to the model. We will just teach it to give the correct answers. It doesn't matter if it ends with hash or box, whatever. So because of that, we cannot depend with this hash ending, but we will use it within the data set to get the ground truth. So we will use this regex answer.re to search the text, and if there is no match, we will return none, there is no answer, or maybe we truncated the answer out of the data point. If there is an answer, we take the group 1. What it means is that in regex, it will take the group that follows these hashes. So it will just return the thing that followed by hashes to us. And we normalize it with the function that we just defined. So if the answer is like hash space 1, 2, 3, it will just return us 1, 2, 3. So that is the idea with this. Next, we will have a function called extract final answer text. So this is more of a flexible final answer extractor. So it doesn't have to end with 3 hashes. It can, but it doesn't have to. So we will we will extract the most likely final numeric answer. So we will do a couple of extractions. So this is for safety, there's no text, return none. And first we do the same search as the previous one. We check the hashes. If they're in here, we return it. Otherwise, we check out this regex, which just checks the other combinations, whatever this regex is doing. And if there's a match here, again, you return the group 1. And if you were not able to find anything so far, we call this number RE bad boy. So what it does is that it just extracts every number within the string and puts them into the list numbers. And we just take the last one out of numbers. So the idea is, if we couldn't match with these, let's take all the numbers, and the last number is probably the answer. So that is the idea with that. And if it doesn't match at all, like there's no numbers or anything, it will return none. Next, we need to have a function to tell us if the prediction is correct or not. For that, we have to compare prediction with the ground truth. So if there is no prediction, we return false. And what we are going to do is we are going to actually subtract prediction from the ground truth and see that if it is less than this error margin. So what it is doing is that we did a lot of normalizations and things like that. And if the answers may differ by a decimal or something, in that case, it is still the same answer. And if their difference, so if the difference is less than this, we can say that yes, there is like a small drift because of some operations we did, probably. But essentially, the answer is correct. This is what it does, instead of just checking if they are strictly equal or not. And if there's a problem with this operation, we just return an except block. But this is just defensive coding. I don't think this will trigger because this is perfectly fine. So this is just defensive. If you like, you can remove this try except block. We have another function to return us if the answer is actually true or not. This will combine extract final answer and answer match functions. So it just takes the actual text that the model generated and the ground truth, which is the actual answer, and it will get the predicted answer from what model generated using this flexible extractor, and then it will just return if it is the correct answer or not by using this answer match function that we just defined. Now, before going any further, I want to quickly run this script and check if everything is correct. I suggest you do the same too, and do it like time to time to check if everything is correct for your case. For me, I already know this works, and I may just get carried away. So in that case, just do your regular checks. For that, I will add an if name equals to main, so that we call the main function, and I go to the terminal. So if you are in this post-training repository, you will just run this command, uv run extra q.python tutorials GRPO minimal pytorch.py. If you are on another repository or any standalone file, just do uv run or python or whatever you are using. In my case, this is the command. So if I hit enter, I should see the parameter counts. And yes, so we applied LoRa, training mode LoRa. We have 4,400 trainable parameters out of 500 million. So this makes sense because our model is 500 million model too. So main function works. We have the helper functions, and now let's actually implement the data set. And still the boring part, but if you're doing LLM training, again, you have to have a data set. Let's name our dataset class GSM 8K GRPO dataset, which will tokenize and hold GSM 8K prompts and answers for GRPO. So with a PyTorch dataset, remember we need three things: init, length, and get item to get the item at the index we provide. So let's start with init. We will have list called samples where we will store the elements. We will count as skipped, so we may skip a data point for several reasons. Maybe the answer doesn't exist inside, or it is longer than the maximum prompt length that we set in the beginning. So in these cases, we skip that data point and we want to keep a count on how many data points that we skipped. So we will use this load rows function that we defined in the beginning. It will just load the dataset subset, and whatever split there that we are using, and it will return that. And we will just iterate through that, and let's actually check what is inside row by just printing the row. And let's just create this dataset class and let's see how it works. Let's also put a break in the end so that we won't see like a bunch of rows. Only one row is enough. And at the end of the main, let's just call this dataset GSM 8K GRPO dataset tokenizer, and we give the max prompt length. Split is the dataset split already, so it is fine. And let's see what's inside the row. Let's come to the terminal, and again let's run the same command. And this is inside the row a question, which is the question. So how many clips did Natalia sell altogether in April and May? And we have the answer, which is the full answer, not just the final 72. So looking at this, we will need a couple of things. First, we need to extract the question, we need the answer, and additionally we need the ground truth, which is 72, because that's the answer. But dataset doesn't provide this to us in a separate field, so we will extract it with using the helper functions that we have defined. Okay, and now let's remove this GSM8K calling because we won't use it, and let's remove the prints too. So let's extract the questions and answers from the row. And now, like we mentioned, there is no ground truth within the data. There is just answer, and it's after 3 hashes there is your answer. So we have to extract it somehow, and for that we will use this helper function that we just defined, extract GSM8K answer. It's in here. As a reminder, it just extract the answer that is after these 3 hashes. We have the ground truth. If it is none, meaning that there is a problematic data set, or maybe it got truncated or something, or we couldn't extract it. If it is none, we skip it and increment the skipped counter. Otherwise, we have the answer, and we apply the chat template. Role is user and content is the question, which will be our prompt. We don't want to tokenize it, and we want to add generation prompt because we will ask the LLM to generate text based on this prompt. And then we tokenize it. Actually, I think you can also put this tokenizer through instead of this, but this is how I did it. And the length of prompt IDs is greater than equal to maximum prompt length that we defined in the beginning, which is 512. We skip it. And the reason for this is, let's mention again, if the prompt is too long and the answer is too long, we will have out of memory. So I implemented a mechanism to prevent that, and 512 is an upper limit for GSM8K in terms of length, so it is a fine number. If you have a stronger GPU, you can also increase it, but 512 is perfectly fine and it works. And yeah, if it is greater than 512, we skip it and increase the counter by 1. Now we have everything to the samples, which will contain the data points. We append the prompt IDs, ground truth, and question. And that's all we need from the init. The next thing, since this is a dataset, PyTorch dataset, we need the length. Very simple, length of self.samples. It contains all the data points. We just get the length of it. The other thing we have to do is the get item. We will return the element in the position index. And this is also very easy since we have the list here that contains every element. We just say self.samples index and it will return the element you want. And additionally, what we are going to do is we want to split this data set into validation and train splits so that during the training we can keep track of validation scores too. For that, we will implement this function inside the GSM8K GRPO dataset, build train validation datasets. So this is a class method because we will get this actually GSM8K as an argument, and we will do everything under this function, build train validation dataset. And instead of creating this GSM8K dataset first, you will just directly go with train validation split and get the datasets. So we get the class first, since this is a class method. The class is basically GSM8K GRPO dataset. We get the tokenizer. We get the maximum prompt length. This is to feed to the GSM8K GRPO dataset. We get the validation split. This is the ratio. And we get the seed, which is our random seed number. And that's all. First, we create the dataset. We create our class, which takes tokenizer, max prompt length, and split. We don't have to give the split because it is already defined here as the train. So we give tokenizer and max prompt length, and we have the dataset object here. Next, we calculate the number of validation data points we need. So for that, we just multiply the length of dataset with validation split, and at minimum it can be 1. This is for safety. And as you can see, we also just can call length of dataset because we defined this length function here. And we need the number of trained data samples, which is the length of the dataset, and we subtract the number of validation. We will use this random split function that we imported here to split this dataset. So we pass our dataset, we pass the number of train and number of validation data points that we want, and we put a generator. So this is needed. So this is just torch.generator, and we want to put a seed here so that we can have repeatable runs. And let's just print the length of the dataset, how many data points we skipped, length of the train dataset and length of the validation dataset, and the split ratios. And let's just return train and validation dataset. Now we have the dataset object and we can load our dataset, and let's just do it. Let's go to our main function and start by loading the GSM8K dataset. Like I mentioned, we will just directly call build train validation dataset, which will return us train samples and validation dataset. So we pass tokenizer, maximum prompt length, and the validation split ratio, seed, and that's all. After that, we need to load the test split as well, because we will code an evaluation function to actually see how we are performing on the test split. For that, we will use the same thing, test data set. This time we directly want the GSM-8K GRPO dataset, because we don't need any further splitting. We just pass tokenizer, max prompt length, and here we don't want the default split because it will be train. Now we are passing the test, and we have it. Now let's also print the length of the test dataset and how many data points we skipped within the test dataset. Because unlike this train and validation part, within the build train validation dataset we print them, but for the test one, within this, the main class, we don't do any printing, so we do it under here. And let's actually run this and see how it looks like. We will run it with the same command again. And we have the outputs. We have loaded the GSM-8K dataset. None of them skip, so it turns out none of them are greater than 512 length for this tokenizer. So this is good. And we have 373 validation data points, 7,100 train data points, and we have 1,319 data points for the test split. Again, none of them are skipped, so we loaded the full dataset. And congratulations, the datasets part is complete. Dataset is done, but we are still not moving to the actual GRPO part, because there is one more thing that we need to do, and that is model evaluation. So it is so important because it will tell us that if we are actually making progress and how much we were able to increase the benchmark scores. So we have to implement a function so that we can do an evaluation both on the test set and both on the validation set during the training. The first thing we need to do is we have to convert the validation data set into a PyTorch data loader, because we are going to do the testing and the validation in batches. So we didn't do this in the training because essentially we are not using batches in the training. We are only using the group size. And if we used batches, in my case, it wouldn't fit into the memory. In the future, it may be with batches, but now the training won't have a batch. However, the validation and test will have batches. So for that, let's start by defining a class called build GRPO data loader. We will return a data loader, which will take the data set, batch size, we won't shuffle it, and we will create a function called make GRPO collate fn. So it will just process the prompts for us. We will define that after this. And number of workers, I set it to 0, so it will run as the main process. And it is a very cheap operation, so it should be fine. And drop last, what it means is that if the last batch of your data set is less than your batch size, you wanna drop it or not. In this case, if it is less than our batch size, it's fine. So drop last will be false. And that's all. Now let's define the function that we will use in the build GRPO data loader, which is our data collator. So we define make GRPO collate fn. It will take the tokenizer as an argument, and collate fn will be called. So it will take a batch and it will process that batch. And what processing we want to do is we want to pad it on the left side so that it can generate text when their sizes are not equal. So we can use the tokenizer's pad thing, tokenizer.pad. We just give the input IDs and they are inside the batch's prompt IDs. Because as you can see here, we return them as the prompt IDs. And since it is a batch, we want to traverse the batch and return every one of them. Obviously, we want the padding to be true. We want the pad on the left side because we are doing a text generation. And we can return the attention mask. We are working with PyTorch, so return tensors is PT. And we are returning prompt IDs, which are the padded prompts, input IDs as we defined in here. We have the attention mask as attention mask. This tokenizer pad will return it with name attention mask by default because we set return attention mask true. And the ground truth is we will take it from the batch. In the dataset, we return it as the ground truth, which is the answer of that question. So for every sample in the batch, we return that number. And that's it. And as a call, we call return collate_fn, which is the actual function that does the building. Now we have the data loader. Let's actually write the evaluation function. For this, I will call the function name just validate. It will get the policy, it will get the validation data set, it will get the tokenizer, maximum number of new tokens we defined as hyperparameter, batch size, and a description. This is for TQDM. So if you're doing validation, I just put well. And we calculate the accuracy by greedily generating over a batch of data sets. So we will do greedy generation and then we will see if the answer is correct or not. So number of correct answers is 0 and total answers are 0. So we will be comparing them both. We get the device, whether it is CUDA or CPU. And now we will use our data loader function that we just defined. We will give validation data set, we will give tokenizer, batch size, and that's all. So it will return us an iteratable validation data loader. We don't want any grad because we are doing validation. So we traverse through the validation data loader and for some TQDM things to make it pretty. So our prompt tensor is we get the prompt IDs from the batch and we put it to whatever device we are using. So these are just our input IDs. We get attention mask. And now we will go on with the generation. So this is a regular Hugging Face generation. We passed input IDs, we passed the attention mask, we passed the maximum number of new tokens, number of return sequences 1 because we only want one output per prompt. We say do sample equals to false so that it will do a greedy decoding, and with that our results will be replicable so that at each prompt it will give us the same result. Use cache. Since it is a text generation, we want to use KV cache for faster processing and to avoid unnecessary repeated computations. And that's all. Now we have the generated text inside the generated IDs. But there is one thing that we should take into account. So right now the generated IDs contain the prompt itself too. So it contains prompt plus the text generation. However, what we want is only get the generated text, because if we have the prompts, when we extract the answer, it can accidentally extract a number within the prompt. So we want to remove the prompt side from the generated IDs. And for that, we have to get the length of the prompt, and then we will use a tensor slicing to just get the tokens that comes after the length of prompt. To do that, first, let's see the shape of the prompt tensor. It will be batch size and sequence length, but still let's see. And let's actually call this function. Let's go to the main, and as initial test accuracy, let's call the validate. We pass the policy, we pass the test data set, we pass the tokenizer, we pass the max new tokens, evaluation batch size, and description is this is the test before the training to get the test score, so that we can compare what score we get after the training. And that's all. Let's run this and see what is the shape of the prompt answer. So 8 is the batch size and 130 is the prompt length. So what we want to do is keep the batch size within the generated IDs and get every token after the 130th token, so that we won't have any prompts left within that. And how we do that is, first let's get the prompt length. Just as we shown, it is the first element within the prompt tensor. 0th element is the batch size, and this is the prompt length. After that, we have the completion IDs, which will be, we take the generated IDs, we take the initial dimension as it is. This is what it means. It means that keep everything the same for this dimension. And for the first dimension, we take everything after the prompt length. So our prompt length, and this means that take everything after coming this number. So it will be getting the actual generated tokens. This will have the dimensions of batch size to the number of generated tokens, and of course the generated tokens themselves. So these are the completion IDs, and these are the actual answers generated by the policy. And we have to decode them, which means that we have to get them back to the actual text format. Here they are still numbers, they are still tokens. We do batch decode so that they turn back into text. We do completion IDs, and we want to skip special tokens such as padding and end of the sequence. And then we can actually start calculating how many correct answers we have. For that, we will sum up, and we will use is answered correct, the helper function that we defined previously. So we will give the text and grant truth, and it will return us whether the text contains the final answer or not. Sorry, it will contain the grant truth or not. And for that, we will iterate the text and grant truth within the completion texts, which are the batch of texts that we just generated, and the grant truth within this batch. And then our total answers will be the length of this batch. It can be batch grant truth, it can be batch prompt IDs. The important thing is that we get the length of that batch, and it will be in the total answer. So So for example, right now, if within this batch, if we had 4 correct answers, this will be 4, this will be 8. And after the next batch, if there are 2 correct answers, this will be 6, and this will be 16, and it will continue getting incremented like this. After we go through all the batches, if we couldn't get anything right, we will just return none. But that won't happen because we will actually have a training loop that works. And then we will just return the ratio of correct answer to the total answers, which will be our GSM-8K score. And let's get to our main function actually. So we already called this. And let's print the result of the test accuracy of the model that we loaded, which is the regular current model before any training. And let's do a test run with it. Now let's go to the terminal and run our command to run the script. And as you can see, it started running the evaluation on GSM-8K dataset. So let's wait and let's get the initial test results and verify that this validation function works. For me, it takes around 10-15 minutes. And once it's done, let's meet here again. Now the validation is complete, and GSM-8K test accuracy before training is 0.3472. And congratulations, you implemented the evaluation script as well. One thing I like doing is that I want to get also the validation score before the beginning of each training. It just gives me a better idea on how the validation is changing. So what I do is, for that, I will say if evaluate every is not -1, meaning that we want the validation evaluation within the code, we will get a validation accuracy by again calling the validate function, just like we did with the test. We give policy. Instead of test dataset, we give validation dataset, tokenizer, max new tokens, evaluation batch size, and by default description is validation already, so that's good. And we print the validation accuracy. Before moving on to the training loop and actually the GRPO algorithm, there is one more thing that we need to do, and that is defining a reward function. So let's go here again and say answer rewards, which will get rollout text and grant truth. I will store the rewards inside this rewards list. And for every text in rollout text, we use the isAnswerCorrect function to compare the text with the grant truth. If it is correct, it will return us true, otherwise it will return us false. And if it is correct, we append 1 as the reward, and if it is not correct, we append 0 as the reward. And we return the rewards list. So this is how I designed this reward function, which is very simple. It just returns binary rewards, 1 or 0. But what I encourage you to do is try with different reward function designs. Try different things. Maybe instead of binary reward, use a formula to generate the reward. Maybe combine multiple reward functions, incorporate the length of the rollout within that, and see how the actual training changes. I think that this would be a good observation and a good exercise. We have the datasets ready, we have the data loaders ready, we have the reward function, we have the evaluator. Now it's time for the big moment. Now we will move to the actually doing the training, you will move to the GRPO and the training loop. When implementing things, the most important thing that I find out is keeping track of the dimensions. For that, I created a notation which is tensor dimension notation. So when I put the shorthand G, it will be the number of generated rollouts in a group. When I put the shorthand P, it will be number of tokens in the prompt. Shorthand L will be number of generated completion tokens, excluding the prompt. So this will be only the tokens that the model generated. And V is the number of tokens in the vocabulary. With that in mind, we can continue starting the training loop. So we will do a couple of TQDM things to make it look pretty, which is this terminal columns. This is for the progress bar. Total steps, if you set a number of iterations higher than the train samples, the maximum iteration will be train samples in this design of the training. And we have the progress bar. We track the number of completed steps in this variable. And we go inside the training loop, which we have our step, which denotes the number of steps we are in. And we have the sample, which what contains the data. And if step is larger or greater than the number of iterations, which means that we have completed the training, we break it. And now let's get our prompt tensor, which will be inside sample prompt IDs. If you look at the dataset we defined, you can see that we return the input IDs for the prompt as prompt IDs. So sample is an element of that dataset. So we take sample prompt IDs will be the input IDs for the prompt. We use the torch long as the data type. This is a convention to represent input IDs. So even if you don't set it to torch long, I think it still makes it torch long. I'm not 100% sure, but it is just good to set it like this. And device is CUDA. We are doing a GPU training. And we do a squeeze 0. So what it does is that it adds a dummy dimension to the beginning. We need this because, like I mentioned, we are not doing a batch training, but when we will generate rollouts from this prompt, Hugging Face will expect a batch dimension from us. So we put that in here. In the end, we have the dimension 1 to the P. The 1 is what we added as the dummy dimension, and the P is the dimension of the prompt. And what I also recommend you to do is, while following this, just go here and print the shapes, like print prompt tensor, and see actually what are the shape of the tensors. I write here because I already did this coding and I'm repeating it for you, but you haven't done it. And I think seeing the shapes on your own is a pretty good exercise, and it makes it easy to learn things. Just print the shapes and just try to guess what will be the shape of the operation that we are currently doing. So I won't be printing because, like I said, I already know and I already write the shapes in here, but I suggest you do this. You can just comment out the initial test and initial validation and just get to see the shapes on your own instead of just reading it. And let's remove this. Take a look at the pseudocode again. I will try to put it into somewhere here in the screen, but you will see in the pseudocode that the first thing we should do is generating rollouts. As a reminder, what rollouts are is that we have a single prompt which we store it inside the prompt tensor here, the tokenized version input IDs of the prompt. So what we do is that within that single prompt, we generate different answers. We generate that group number of times. So for example, we have the group number 4 right now, and from the given prompt, we will generate 4 different answers from that. And with these answers, we will calculate different things for the GRPO, such as reward and advantage. So let's start by generating these rollouts, which is the first step. For that, we will define a function called generate rollouts. We will give policy as the argument, prompt answer, group size, max new tokens, and tokenizer, and it will generate us the rollouts. And within the rollout, we will actually do some prints to show you how the matrices look like. For that, we will do a couple of things. First of all, I will put a break in here so that we can debug one step at a time instead of having like this chaotic terminal outputs. And I will also comment out the initial test and validation for now so that we can quickly run this command. Now let's go here and start generating our function, define generate rollouts. We have the policy, we have the prompt answer, group size, max new tokens, and tokenizer. The first thing we will do is, since we are working with prompt answer, which is our input, we want to have an attention mask for that. So we will use Hugging Face's generate function, and actually we may not have to give a prompt attention mask. So this is an attention mask filled with ones. This is what torch ones like do. Returns you a matrix filled with ones with the same shape as the prompt answer. So what it is going to say to the generate function is that allow every token attending to every token. So it will just tell that actually there is no mask in here. So this what this mask does. So without it, I don't think it will be a problem, okay? But sometimes there can be ambiguities, and this is just, I find it a safe practice to say to the function that you can attend to all token, which is what we want. And maybe if there's an edge case that we couldn't think of right now, so this prevents all of them. So we will do generation. Let's do again with torch Norgrad. And again, like we mentioned, we use policy.generate. We put the input IDs at prompt answer. We put our attention mask, which is just filled with ones, just telling that every token can attend to every token. So there is no, it actually explicitly says that there is no masking. We have the maximum new tokens, number of return sequences. So since we want to generate group size times of answer, we pass group size as the number of return sequences. This just tells this function how many answers you want to generate within this single call. So we want to generate group size times of answer. We want to do sampling. So why don't we do it greedily? And we talked a lot about we want this to be reproducible at everyone's computer. But then why we are doing sampling in here? If we don't do sampling, all the responses for the group size will be the same. As a result, every reward and every advantage would be the same. So there won't be any learning going on. Within the group, we want to have different responses so that every response can look into the group and say that I am better than this response, I am worse than this response, and hence can create this useful learning signal. For that, we need different generated answers. For that, we do sample true. I set temperature 1, top P1, and since this is a generation, we want to use KV cache, so I set the cache true. The dimensions of this will be, we are returning group size number of responses, so the first one will be G, and remember what L is. L denotes number of generated tokens, and P denotes the length of the prompt. So as a result, it will return us prompt plus the generated tokens. So our returning matrix will have the shape G, P plus L. Now what we want to do is we want to isolate this L, and we don't want to have this prompt. So we are only interested in the generated tokens, because this is how we are going to apply the formula zone, only the generated tokens. We don't want the initial prompts. We do the similar thing that we have done previously. To isolate that, we get the prompt length, which is the prompt tensor shape 1. Remember, the shape of the prompt tensor is 1 to P, so if we get the first dimension, it is P. And the completion IDs, which are else, we can get it by putting this here, which will get everything within the 0th dimension. So it will get everything within the G, it will stay the same, and for the for the first dimension, which is L, it will get everything after the prompt length, which will be L. So our completion IDs, which are the generated token IDs for the generated answer, will be inside completion IDs with the shape G to the L. So the next thing is, first of all, we need an attention mask, an actual attention mask this time. So what I mean is that we should specifically put attention 0 to the pad tokens and end of the sequence tokens after the initial end of the sequence, because we don't want, when we will calculate the log probabilities, and also in the end when we are calculating the GRPO loss, we don't want them to be included into our score, and we don't want to attend to them. But we should also get the initial end of the sequence token in the generation, because what it means is that it is a part of the generation, because we expect the model to generate end of the sequence model in the end. So what we want to do is we want to put a mask on every pad and every end of the sequence token ID apart from the initial end of the sequence token ID. In theory, there should be only one end of the sequence token that comes after the generation ends. But sometimes the pad token ID is the same as the end of the sequence token ID, and the tokenizers differ a lot. So again, for safety, what we are going to do is, first of all, we are going to get every end of the sequence token and pad tokens. We can do that easily. We get the completion IDs, and this checks if it is equal, it returns true if it is equal, and false if it is not. So we get the completion IDs metrics, and if they are equal to end of the sequence token ID, or they are equal to pad token, it will return true, otherwise it will return false. So this end of the sequence or pad will be a matrix that consists of trues and false, and every true will be for the end of the sequence token ID or pad token ID. Let's actually print this and see how this matrix looks like, because it can be a bit abstract otherwise. Let's run our command. And if you look at here, you will see something interesting. The first three groups are all false, so they haven't generated any pad or end of the sequence token ID. which means that they hit the maximum new token limit before they complete the generation. So this is also expected. We expect these things to happen. And in this case, not the best scenario, but in this case, in our training, it is fine. And most likely it's also because we extract the answer with the number that get generated to the last. So even though it doesn't reach to the final answer, we can still get that number. But we may also not get, okay? Like I said, this is not the most optimum thing. And usually in these cases, like there are some solutions. You can increase the maximum new token length, which I can't because it hits the memory limit. Or you can define your reward function in a way that handles this. Or you can keep track of like how many of them you get truncated, which I show it in the like actual post-training lab repository. I logged them. But in our case, for our case, it didn't hinder like the training. It didn't cause any problems. So we will just say okay and continue like this. And since this is for educational purposes, it will say we are okay with a small maximum new tokens. But just keep in mind that this can be a problem, okay, especially if you have binary rewards. Because if your rollout didn't generate the actual answer because it didn't have the limit, then it will receive a 0 reward. Okay, this can be problematic. And if you look at the last rollout of the group, you can see that in the end, these are true. So it actually hit the end of the sequence token and it generated the rollout that it wants. And the pad tokens and end of the sequence tokens are true. So now what we want to do is we want to get the first end of the sequence token. What we can do is we can apply the CumSum. What this does is it sums up everything and it does it cumulatively. So for example, you have a list 1 through 3, it will start summing up. It will be 1, 3, 6. So it will sum up everything before that and put it into there, that index. So in PyTorch, it will treat false as 0 and true as 1. As soon as it hits the 1, so as soon as it hits the true, it will stay as 1. And after that, it will be 0. So this is what it means. If it is less than or equal to 1, those will be true. So until the first end of the sequence token, they will be true. And after that, it will be false, which is the exact mask we want. After the first end of the sequence token, they will all be false. And we want to convert those true falses into ones and zeros. And we can do that with long. And let's actually see this completion mask in the terminal too, so that it is more concrete. So as you can see, these are all ones, which is expected because they don't have any end of the sequence token ID. And when we come here, they turn into zeros. It is not visible in here because this is just like a big vector. But the first end of the sequence token is also 1 because we set this one. And then we return completion IDs and completion mask. Let's remove the print statements. And one thing is we don't need this. We only return 2 things. And let's remove the break. And that's how we generate rollouts. You have the generated rollouts with G to the L shapes and the rollout masks. Now if you look at the pseudocode again, you will see that the next step in the process is getting the log props for the reference and the policy model. So how we are going to do that is we need a function to get the log props. So let's create that function. Let's go here and let's name it token log props model to get prompt IDs, rollouts, and the rollout masks. Briefly, what we want to do is we will get the prompt IDs, which is the prompt. We will get the rollouts, which is the generated text. And first of all, we want to merge them so that we will have the IDs for both prompt and for the generated text as well. So we need it because we will feed this to the model again to get the logits. What these logits will be is they will return us probability of a token generating the next one. So it will return us a vector of vocabulary that contains scores for generating that token in that vocabulary. So the important thing is, since this is a next token generation, the token at the position t, for example, gives you the distribution over the vocabulary for the position t plus 1. So if you want to get the distribution for the t plus 1 token, we have to get the logits for the tth token. So we will have to shift the logits by 1. Okay, so this is what it means. So we want to get the distribution for the generated tokens, we have to shift everything 1 to the left. So we have to start from the last token of the prompt, because that will give us the distribution for the first token of the generated text until excluding the last token of the generated tokens. Again, we exclude the last token because the token before that will give us the distribution for the last token, but the last token will give us a distribution for the token after that, which we don't care because it is not generated. So we will cut it there. So we will take it until the last token. And then what we have to do is we will have this matrix that has the vocabulary distribution for every token. We have to go for every token that is in the rollouts, and for that token position, match it where it is in the vocabulary, because the number that is in the vocabulary will be the log prop of that token. So it is a bit abstract, it may be a bit confusing, but as we go through, I will try to explain it and make it more clear how we do these operations. So the first, like I mentioned, we have to merge the prompts and the rollouts. So the rollout shape is G to the L, but initially prompt IDs is only single prompt with the shape 1 to the P. We want to copy it G times so that we can actually add these two together. For that, we will use the repeat interleave function of PyTorch. It will just copy those values within the dimension 0 this times. So the rollouts.shape is G, so we want this to copy the prompt IDs G times along the dimension 0. And it will return us a matrix with shape G to the P, which is what we want. We have G times prompt IDs. And then like we mentioned, we merge the prompt IDs with rollouts. We can just say torch cat, which is concatenate. We give the prompt IDs extended, what we just calculated, and we give the rollouts, and we want to merge them alongside the dimension 1. So it will just add them after each other while keeping this dimension. So we will have a matrix shape G to the P plus L. Now we have the input IDs that we will feed. Next thing is we want to get the token generation distribution over the vocabulary, which is the logits. To do that, we will just feed the complete IDs to the model. We don't want to use cache since it is not a token generation, text generation, and we get the logits. It will return us a matrix with the shape G, which is the group size, P plus L, prompt plus the generated text, and the vocabulary. So for every rollout within the group, for every token, we will have the vocabulary distribution within the logits. First, let's get the prompt ID's shape, because we will again remove the prompt. So the question is, if we are gonna remove the prompt again, why did we put it in the first place? This is because of the shift that we are going to do that I mentioned in the beginning. We need the vocabulary distribution of the last token of the prompt IDs such that it will give us the actual distribution for the first element of the generated text. Because of that, we have to store this again. And we do the shift. So we get the logits. The first one just stay as the same. And within this P plus L, we get the last token of the prompt, because it will generate the first token of the text. And we take it until the last token. We don't take the last token because what it generates is, we don't care, because it is out of the context. And for the vocabulary, we get everything we get within the vocabulary as it is. We get this and we call this logits shift. And to this, we apply the logarithmic softmax, which is what the log props is. So this does it for us. Basically, it first applies the softmax, which converts every V into a probability distribution. Why V? Because we set the dimension to -1, and it gets the logarithm of that. And we will use this within both the surrogate function and the KL penalty calculation. We already discussed why we use logs. If you want to know, just go back to the beginning of the video where I explained this GRPO as a whole. Now, what we want to do is, so this GLV contains the probability distribution over the vocabulary, and we already have the rollouts which has the generated text, generated tokens. So what we want to do is that we take that token ID within that position in the rollout, and we want to go into this log props to that position. Let's say that the position is 112. We will go to the position 112 within this matrix for that token in that group and get that probability, and that will be the log probability for that token. And how we are going to do this is we will use something called fancy indexing within PyTorch. So there are a lot of ways to do it, but for me it was the most intuitive. So what we will do is, first we will create a matrix that has the rollout shape 0, which is the shape of G. So it will be a matrix that starts with 0, 1, 2, 3, 4 and goes until the G. This is what torch arrange does. And we want to unsqueeze it. It adds a dummy dimension to the end. We need this for fancy indexing. And we need to do the same for the position indices. In that case, the position indices are rollout shape 1, so it is L. It will again create first a vector with the shape of L, and it will consist of numbers starting from 0 to L. And we add a dummy dimension to the beginning of this matrix. And then when we say the log props, we can do the selection like this. We select the group indices, we put the position indices, and we put the rollouts. And when we do this, for every group index and every position index, it will go to the number in the rollout, which is the token ID, within the v vector, and returns us whatever number there is, which is the log probability. And since for every vocabulary we get a one number, in the end we have a dimension of g to the l. There is no v. So what we did is actually we replaced the token IDs with the log probabilities. So this is what it does. And then one more thing we should do is we should apply the mask. So remember, we return the rollout mask where the masks are 0. The mask that we want, basically what we don't want to attend, are encoded as 0. The things that we want to attend are encoded as 1. So to remove the things that we don't want to attend, we can simply multiply them both. So we say selected log probes mask. We just multiplied selected log probes with the selected masks, and those zeros will remove everything there while keeping the others. And we return selected log probes masked. Now let's come to the main function and let's actually call this. We start with torch nor grad, since we are not doing any gradient operations. The old log probabilities will be token log probes, policy, prompt tensor, rollouts, rollout masks, and it will return us this matrix that every element contains the log probabilities of that token. And we did this for the reference as well. Reference, prompt tensor, rollouts, rollout masks, and that's it. Beginning, they are the same because this is the first step and we haven't done any gradient update yet, and that is normal. So this is how you calculate the log probes and take them initially. So I think it may be a bit confusing in the beginning. Okay, so I suggest you to watch it like several times, the implementation of this token log probes function, and try to see, like, print this group indices, print this log probes, see what is inside, and then it should start making sense. Actually, most of the implementation is complete by now. We have the helpers, dataset, log probes, we have the rollouts. What is left is we will just follow the pseudocode and implement the mathematical formulas that we discussed in the beginning. First things that we will do is we will calculate the rewards for this group, and then we will calculate the advantages. Let's start by calculating the rewards for this group. First thing we do is we have the rollouts, but they are not text, they are tokens. But the function that we defined to calculate the rewards, if we go into that function, answer rewards, you will see that it gets rollout text as the input. So we have to convert these rollouts from tokens to text. And how we can do that is just tokenizer.batch decode. We want to skip special tokens such as pad or end of the sequence. We want to get the text only. And then we will have a list of text, the text that are the rollouts. So they will be the generated text that we got from the prompt. And our ground truth is within the sample ground truth. And we can calculate the rewards by calling that answer rewards function that we just discussed. We provide rollouts text and we provide the ground truth, and it returns us the rewards. I specifically set the data type to be TorchFlow32, and the device should be the same device as the rollouts, which will be GPU. and this will be a tensor of shape G, which is the group size. Now let's calculate the advantage. I will put the formula of the advantage again to here as a reminder. So what it is for every reward that we want to calculate its advantage is we take that reward, subtract the mean of the rewards within that group, and divide it by the standard deviation of those rewards, and we add epsilon to it. So of course, within this, we don't do it one by one. We do them as matrix operations. So here it will be rewards, which is a vector of size G that will contain all the rewards, and this will do all the matrix operation for us. So instead of doing one by one, this will subtract this number from every element, and this will divide the matrix by the standard deviation for every element, etc. And we have our advantages ready. So this advantage, remember that it is the main learning signal that we will build everything upon. We want to add a dummy dimension to the end by 1, and in short time you will see why we do that. And let's slowly go into the second loop, which is the PPO epoch loop that you'll see in the pseudocode. This is where we will do the actual gradient updates by PPO epochs number of times. So let's store the losses inside this list. And let's just iterate through the PPO epochs. We start with optimizer 0 grad. This is a PyTorch training. First thing is we have to calculate the new log probabilities. By the way, everything is, as you can see, one-in-one same with the pseudocode. This is what I like about this, is that this pseudocode is so implementation focused, and the formulas are so implementation focused that we can just look at it and see how we need to implement things. And when we understand how things are working and we combine it with these like frameworks, everything becomes just crystal clear and easy to do. So this is what we are doing. Again, if you look at the pseudocode, we start by getting the new log probabilities. We get the ratio of the surrogate function. I will also put the formulas to the screen as a reminder when we go there. We take the ratios to calculate the surrogate function, and then we calculate the surrogate function using the ratios and advantage that we calculated in the beginning. And what you will realize is that we have a single advantage per rollout to keep in mind. Then we calculate the surrogate with this ratio and advantage that we calculated. Then the second component of the GRPO loss is the KL penalty. Then we will calculate the KL penalty by the log probes that we already calculated. The next step is we calculate the loss value by taking mean of the minus surrogate plus KL coefficient multiplied by the KL penalty. Then we update our policy, which is loss. Apart from what is in the pseudocode is that we will save the model, we will print the loss values, and things like that additionally. So let's go by step 1, calculating the log probabilities of our current policy, which will be the new log probabilities. Why new log probabilities? Because we will update this every time within this loop, so that it will actually become different than this old log probabilities. Even though we put the policy inside both of them, this policy will no longer be the same after the initial iteration. We pass the prompt tensor, rollouts, and rollout masks. You know this already. Now we go with the ratio. Like we mentioned initially, new log props and log props are the same. So initial ratio, which is the torch exponential of new log props minus old log props, will be the same. I'm putting the formula to the screen as a reminder of the ratio. Why we are using the exponential, why we are subtracting them. To learn about it, go to the beginning of the video where I explained the GRPO. Let's calculate the unclipped version of the surrogate. So this is the leftmost side, which is just ratio multiplied by advantage. And when you look at here, we are multiplying ratio, which has the shape g to the L, with advantage, which has the shape g to the 1. So this is why we added this dummy dimension. So what this does is that it multiplies the advantage value with every token L within this ratio. So first rollout has an advantage value, and we multiply every L within that index with the advantage value. And PyTorch takes care of broadcasting within this multiplication. We do that because we have a single advantage value for rollout. And then at the end of this, we have the first ratio and advantage multiplication. Now we need to have the clipped version that we can just get it by torch.clamp. Again, look at the surrogate objective, which is we clip the ratio 1 minus clip epsilon, 1 plus clip epsilon, and then we multiply it by advantage. Again, it has the same shape, and then we get the minimum of these two values, and this will return us our surrogate value. Now our surrogate function has been calculated. The next step is the KL penalty. To do that, we will need the log prop difference, which is the difference between the reference log props and the new log props. And also remember that with the scale penalty, we are actually doing an approximation. And the KL loss is, when you look at the formula again, I will put it into here, is basically exponential of reference log props minus new log props, which is the log prop difference, minus log prop difference minus 1, which is exactly what we did in here. Now we have the KL loss, we have the surrogate. The next thing is we will combine them to get the final loss. First, let's do the formula inside the mean, which is minus surrogate plus KL coefficient multiplied by KL loss. However, there is one more thing, is that we padded the rollout masks because they were not the same size. So because of that, we have to multiply them by the rollout masks. Otherwise, when calculating the mean, those mask tokens will also add up to the loss value. Next thing what we are going to do is get the mean, actually. And also if you look at the final loss formula, you will see that we divide by n, where n is the number of tokens. How we get that number of tokens is that basically with rollout masks, that's sum. Because rollout masks contains 1 for every token that we use, summing them up will give us the total number of tokens we had in the beginning. And GRPO loss inside is a matrix. So we want to calculate everything, get the sum, and when we divide it by the number of tokens, we have the mean, which is the loss value. The clap min is just in case it becomes 0, if we only have masks, which is edge case, which won't happen, but this is just for safety again. And then we just do a gradient update. We do a gradient normalization clipping. So this is just a training thing in case the gradients do explode. For that, we put the trainable parameters, max normalization, and that's it. We take the optimizer step. We append the GRPO loss to the PPO epoch losses, the list that we defined in the beginning. And that's it, and then we just keep track of the steps. And this was the GRPO. The next things that we are going to do is just like printing the loss, putting the TQDM, saving the checkpoints, doing the validation, etc., which are also important. So bear with me. But also congrats, because you actually did the core GRPO training implementation. Also, we are going to do the actual training. We will run this and we will see how the validation and test scores are going to change. We will also do a text generation on a prompt where the model were not able to get the answer right. And we will show that after this training, the trained model will be getting that answer right. So bear with me. We get mean loss by torch stack, PPA epoch losses, mean, float, and we get item. We put the TQDM's progress bar description and update mechanics. If evaluation turned to be true, which is greater than 0, it is the number of steps that we wanted to be evaluated, and completed steps is divisible by that, which means that we are at that step that user wants to evaluate. We will say validation accuracy, and basically we will run the validation function with the validation dataset. And we will write the validation score to our progress bar. And if user wants to save the checkpoints, and we are in that step where user wants the checkpoint to be saved, we just save it, and we save the policy to the checkpoint path. And we also save the tokenizer. And we print that we save this checkpoint step to this checkpoint path. And we close the progress bar. And let's say that we are at the last step, but we didn't save it in the end because the save array was not perfectly divisible. So in that case, this is what I thought, this is how I designed, is that even though if it is not in the perfect save every step, we want to save the last checkpoint. And we save the policy, we save the tokenizer, and we print that, we save this checkpoint. And in the end, we get the final test accuracy to see how much we improved the test set. So for that final test accuracy, we again call the validate function. We give the policy, test dataset, tokenizer, max new tokens, evaluation batch size, and the description is test after training. And that is it. And we are going to print the initial test accuracy and final test accuracy. So it is complaining because we commented it out for debugging. Let's comment this out again. And it's not complaining anymore. And actually this is the whole training loop that I'm going to show you. Now you have the GRPO training loop that you coded yourself and you understood how it works in detail. It is time to actually run this script and see the test values, the loss values, and see how much it improves. So we will run it for 200 steps. I have 16 GB of memory in my GPU. For me, I think it takes like an hour at max. So I will start it now. Let's go to the terminal. So I'm going to run this script with the command within this repository, which is uv run extra-q.python This is inside tutorials, GRPO minimal PyTorch.py. So whatever repository you are at, just modify this according to you. If you are inside this post-training lab repository, you can just use this as it is. Let's click enter. And it started with doing the initial test. Now I will pause the video and let's wait until the training is done, training is complete. Let's meet you again after and check out the results. And the training is done. It was a small 200-step training, but we can see that the accuracy, the validation accuracy has increased overall, and test accuracy increased from 0.3472 to 0.3821. So this test accuracy verifies that the GRPO training has worked, and it actually increased the GSM-8K accuracy. And now let's check the saved checkpoints. In my case, I saved them into the under checkpoints, tutorials, and GRPO minimal PyTorch. So here you will see the steps, step 100, step 200. We only did 200 steps and saved it once every 100 step. So in my case, here is the train model as well with its adapter and the tokenizer. Now let's do one more thing. Let's actually generate a text. Give it a prompt that the model was not able to get correct before the training, and a prompt that it is able to get correct now after just 200 steps. For that, I will use this script. I will put a link to this code in the description, but if you're under the post-training lab, it is under CUDA backend and generate text.py. So here it is. It's like a very simple code. It just loads the adapter to the base model, and we have a bunch of arguments here, and it generates the text. If you are under the post-training lab, you can just follow the exact commands because you should already have the script. If not, I will put a link to this code. You can just copy and paste it into your working space. Initially, let's run with the regular model. So if we don't select anything, it will just load the Qwen 0.5b instruct model, which was our base model. And I got this prompt from the GSM-8K test set. Grandma Jones baked 5 apple pies, blah blah blah, etc. And the answer for this prompt is supposed to be 26. So let's try it with the base model. And it is giving us the answer 186. Now let's try with the model that we just trained with our own GRPO implementation. So as you can see, I'm loading the adapter, and the model path is, this is where I saved, checkpoints, tutorials, GRPO minimal PyTorch, step 200, and the same prompt. And now it is able to give us the correct answer after just 200 steps of training. So we verified it by the test benchmarks. Also, we verified it by generating a simple text. And now you know how GRPO works. You implement it on your own. You implemented the evaluation part as well. You did the evaluation, you did the text generation, and congratulations for all of it. Now what to do next is, I would suggest that just play with this, like this reward function. Take a look at how the values are changing, how the advantages are changing, how the rewards are changing, etc. Just follow the training more closely. do it for more number of steps. Try with different data sets, try with tool calling maybe, and try to get a better grasp of things. Also, you can do it by just coming to this repository, and under the CUDA backend, this GRPO train is exactly the same as what we just did. So I created the script that we created together based on this. This version is just more modular, so there are more .py files, but it has more transparency. What I mean is that, for example, it has TensorBoat logging, it is logging more values, etc. So if you want to track things, if you come here and run this GRPO train Py, it would be more beneficial. And the logic is the same, so you know how it works already. So it wouldn't be some different script for you. And plus, if you want to change things within that, you already know how they work as well. You already know how the reward function works, and this and that. So you can easily do it with this too. And that's all for today. So thank you for listening. Thank you for taking the time. I hope you learned something new. Don't forget to like this video, subscribe to my channel. What you want to see next, let me know in the comments. As I mentioned, I will put a link to this code in the description, the GitHub link, also to this generation function. Basically, you will find everything within the description. And see you at another video. Bye bye.